The previous title I proposed was something like almost 2 years ago. And today I would like to tell you about some haute frequency pairing around magnetic impurities in a superconductor. So, well, let's go back to superconductivity, and one of the key quantity is the pairing functions, which is defined by these equations. So the pairing between two electrons, the position R1, then T1, and another electron at position R2 and position T2. And under exchange of the two electrons, it must satisfy if I exchange R1 and M principle. And therefore, because of this exchange of time, there are two conventional pairing you can conceive. The conventional of T1, T2 is F alpha beta of T2, T1, but also you may conceive some haute frequency pairing where you have a minus sign for these functions when you exchange the two-time ordering. And this was, well, first predicted almost 50 years ago by Berezinski, and he wanted to apply that to helium-3, but it turns out not to apply. And since these, well, 50 years, there has been a lot of work on this haute frequency pairing. And why, when you conceive this haute frequency pairing, where to find it? So let's assume that the electrons has 3 degrees of freedom, orbital degrees of freedom, some spin degrees of freedom, and this time ordering, this frequency degrees of freedom. And you must, the product of the three, you must get something out for the pairing function. So therefore you have these three options. The standard was even frequency pairing, a spin singlet, and orbital even. That's the standard S-wave superconducting parameter, so BCS, cuprates. But you may also get the even frequency pairing, spin triplet but odd orbital. So typically P wave, for example, or F wave. And this one has been quite popular in the past 10 years. It's the P wave superconductor, which may host Majorana. And you may also imagine that you have some exotic pairing functions which could be odd in frequency, but even in the spin and orbital, or odd in frequency, singlet sector, and odd in orbital. These all have Pauli principle, and the first two are quite popular and obvious, but people have been looking for the last two, at least the OTE, the odd triplet E. So there have been many reviews written on that, a recent one by Linda and Balatsky. And what I want to emphasize in a short word about history, this haute frequency was proposed by Berezinski. And then people have looked for purely intrinsic order parameter with haute frequency pairing, so bulk properties. And this was advocated by Belitz and Kirkpatrick in heavy superconductors based on contour lattice and heavy fermions. It has been followed, so it has a very long history. And I would say that these questions has really popped up in 20 years ago, as people start to realize that we can eventually induce such haute frequency pairing by proximity effect. So typically by considering superconducting ferromagnetic junctions, and then it was realized that these haute frequency pairing are induced in the ferromagnet in contact with a spin singlet S wave, and can propagate far into ferromagnet. So this is the famous paper by Bergeret, Efetov, and Volkov, which was and since then, people have been looking a lot for this kind of pairing. And it was eventually realized that this haute frequency pairing turns out to be rather ubiquitous. As soon as you break spin rotational symmetry or even translation symmetry, so basically as soon as you have some proximitized effect, And basically, you start with a standard Cooper pair with an even frequency BCS superconductor. In proximity of a ferromagnet, it will decompose into some even frequency triplet pairing and some odd frequency triplet pairing mixture. So, and on the experimental side, well, there have been quite a few experiments and on this proximity effect. I think the one I like most dates back to 15 years ago. They consider niobium titanate on top of this chromium dioxide, which is semi-metal or disordered semi-metal. And these niobium titanates are quite far from each other. So in that sense, they realize the Josephson junctions. And they do measure a supercurrent in between these two superconductors, even due to the fact that chromium dioxide is a polarized semi-metal, as you can see here, the Fermi energy, you have only spin up available. So you have only spin up, electrons with spin up that can transmit this Josephson current, and the only options to get a non-zero and substantial Josephson current is to have odd triplet S-wave pairing, which is mediated here. So this is here. This is an indirect but manifestation of odd triplet frequency pairing. Okay, so that's quite a substantial indirect evidence of this odd frequency pairing. And but in the past years, I mean, we've been analyzing with STM a lot this proximity effect between superconductor and ferromagnet. So I just here list a few set of experiments. So the one involving iron impurities on top of lead, which host these elusive Majorana bound states. Also this experiment in Hamburg, where you have iron on top of superconducting substrate, and you evidence H states and a strong density of states along the ferromagnetic island here. And with my collaborator in Paris, we look at similar also systems where we have cobalt atoms on top of lead, and we also find evidence of well, exotic physics and eventually some H states propagating around this age. So this raises an issue: can we actually see evidence of this odd frequency pairing via spectroscopy? To answer that question, since it's quite clear that the physics involving the proximity between ferromagnetic structure and pairing is quite complicated, let's shrink it to the minimum, and in that respect, go back to basics, and let's try to solve a much simpler problem and understand that if I consider a single impurity immersed in a superconducting substrate, can I find signature of such odd frequency pairing? So this is what I want to emphasize and I want to show you. So, well, if you have a single impurity immersed in, for example, in a superconducting substrate like lead, well, you do expect to find some Shiba, U-Shiba within of bound states. Let's assume to describe such bound states, it's convenient to consider the classical spin limit and the impurity being described by, therefore, by a local magnetic field. This is an easy solvable problem, and you find the bound states, which is called a Shiba bound state, which have some electron and hole component of the wave functions. For alpha, which is a dimensionless parameter, being density of states times J times S being 1, you have a finite crossing, and the ground states switch from even to odd. So, well, we've been studying these ground states have been studied to a large extent, and both in 3D, in 2D, it has been proven they have a long spatial extent, which can be actually useful to build more complex structures. So here these are, for example, experiments of my collaborator in Paris, where they have magnetic purity in niobium deselenized, and they found very long spatial extent of the Shiba bond states, which typically is of order of 10 to 20 nanometers. And actually, by also analyzing the oscillations of the density of states, and they can correlate the positions of the oscillation peak to the position of the peak in the spectral gap. So all that to say that we have a very good understanding of this, the behavior of the Shiba bond states, which is quantitative. So going back to my initial questions, well, I need to model a little bit this Shiba physics. So I will work in the rotary in the rotary diffusion Nambu space. And for the Shiba bond states, well, I have a 2x2 matrices, which I can parameterize that way. And I'm interested in these off-diagonal terms, which encapsulate the pairing correlator. So, as I said, I will only focus on what happens on top of the impurities, so I can forget about the orbital degrees of freedom, and on top of the impurity I have two options only. Standard even frequency pairing and spin sequence, or odd frequency pairing and spin triplets, which satisfy these two properties. What we did is that we consider local density of states on top of the impurity, and we can combine the even and odd part of this frequency density of states, provided we keep the energy smaller than the gap H. And you can prove that you have a one-to-one relations between the even part of the density of states and the imaginary part of the odd frequency pairing, times some proportionality constants which depend on the position of the peak. So actually this general proportionality relations between local density of states and odd frequency pairing is quite robust. The Shiba bond state is well characterized, as I told you. It basically depends on two parameters: the magnetic coupling, and which is J, and the potential scattering term, which is V. So well, we get something which are well known, and we can relate this proportionality constant in terms of the position of this peak, E0, and these two dimensionless parameters. To make it in short, basically you have only a very few parameters left, 4 exactly, if you parameterize your Shiba bond states by Lorentzian. This has been used by the group of Katharina Frankel, who displayed the data. U and V are the particle and all component of the Shiba wave functions. E0 is the position of the peak. And still, there is a fourth parameter, which is typically the broadening of the intrinsic broadening of your in-gap Shiba bond state. So 4 parameters only. These 4 can be actually very easily extracted from spectroscopy: the position of the peak, also the broadening, it's thermal one, and U and V you can extract them from the conductance. So therefore, from the height of the peaks. So all these parameters can be extracted from the deconvoluted local density of states, and once you get therefore you have access to the density of states, you can extract directly the imaginary part of the odd frequency pairing functions. So this is what we did with real data. Here we consider lead and silicon 111, and they have a bunch of impurities. So this is a 2D map of one Shiba state at 0 energy. So this is what the density of states look like. Away from, in black, away from the impurity, you just recover your standard substrate density of states and the gap, and you have these two nice peaks, which are two Shiba peaks. So we use a recipe to extract the height of the peak, the width, all that, and from that you can feed them with two Lorentzian, which these are the deconvoluted local density of states on top of the impurity, and then you can extract by this simple Gaussian relation the old frequency correlation function on top of the impurity. So we've been using this recipe to old frequency pair, and if you want to, you can have access therefore to the real by analytic continuations if you wish. We can do that to many other impurities, and this is quite general. What is also important to notice, yeah,
5 minutes,
is that you have a fractional macroscopy. Sorry?
5 minutes.
A macroscopic fraction of the local density of states. Okay, we could go further, but I won't have time to look at the spatial dependence. We also extend this work for dilute set of magnetic impurities, and whatever. Here the physics will be the same, except that the Shiba bound states will be replaced by Shiba bands. But you do have the same proportional relations between this imaginary part of the wave frequency form and the density of states. So this, you can find more details in these publications. Well, this brings me to my conclusions, and I tried to convince you that, even on this very simple system of an isolating magnetic impurity, we can extract some odd triplet correlation functions on top of the impurity. And there is a fractional, macroscopic fraction of triplet correlations of a magnetic impurity. And let me thank my collaborators in that. So the experimental group in Paris, led by Tristan Crène, also Dimitri Roditchev, and students and postdocs in my group, Vivien Perrin, Fabio Santos, and my colleague Marcello Civelli. Thank you.
Thank you very much.
Ready for questions if you have some.